Right now, you're moving at 1,670 kilometers per hour. If Earth stops spinning, you don't. In less than 1 second, the air becomes a supersonic weapon. The oceans rise into walls of water, and everything not anchored to Earth is hurled east at the speed of a jetliner. 5 seconds doesn't sound dangerous. Physics disagrees. This is the first 5 seconds after Earth stopped spinning. To grasp the true scale of what happens when the planet halts, you first have to realize how fast you are already traveling without feeling it. Because of Earth's rotation, every object on the surface carries immense, hidden kinetic energy. Mathematically, your linear velocity depends directly on your latitude, expressed by the fundamental formula where velocity equals rotational speed multiplied by Earth's radius and the cosine of your latitude angle. At the equator, the planet spins eastward at roughly 1,670 kilometers per hour, over 460 meters every single second. In mid-latitude metropolises like New York, London, or Tokyo, that speed is still a blinding 1,100 to 1,200 kilometers per hour. Only at the exact geographic poles does your linear velocity drop to zero. You do not feel this furious motion because everything in your immediate frame of reference, the ground beneath your feet, the atmosphere, the skyscrapers, and the oceans, is moving together in seamless, invisible synchrony.
Then, the cosmic brake is applied. In a single millisecond, Earth's solid surface abruptly halts its rotation. Yet, according to Newton's first law of motion, every unanchored object on the planet retains its forward momentum. In that first fraction of a second, the world experiences an atmospheric shear of apocalyptic proportions. While the planetary crust freezes in place, the fluid ocean of air above it keeps roaring eastward at supersonic speeds. With the speed of sound at sea level sitting at roughly 1,235 kilometers per hour, an atmospheric wall moving at Mach 1.35 crashes over the stationary landscape at the equator. Continuous, continental-scale sonic booms shatter simultaneously across the globe, tearing human eardrums and shattering unreinforced glass for thousands of miles. Humans, vehicles, trees, and unanchored structures are instantly transformed into high-speed projectiles hurled horizontally toward the east. Modern skyscrapers, engineered to handle vertical gravitational loads and horizontal wind shear up to 200 kilometers per hour, are completely incapable of withstanding lateral kinetic forces 400 meters per second strong. Millions of buildings are sheared cleanly off their concrete foundations in a heartbeat. Near the ground, violent mechanical friction between the hypervelocity air and the stationary crust pulverizes concrete, glass, and rock, launching millions of tons of blinding dust into the lower stratosphere that blotted out the sun. Long-distance oil and gas pipelines tear apart under immense shear stress, igniting apocalyptic fires across energy corridors. High-voltage transmission towers and suspension bridges snap like dry twigs, plunging the dark side of Earth into absolute blackness within 3 seconds. Freight trains are violently ripped from their tracks, while massive ocean liners sitting unanchored on the water slide across coastal harbors like rolling missiles. This atmospheric shear behaves differently as you gain altitude. Up at 30,000 feet, where commercial airliners cruise, the jet stream collapses into catastrophic wind shear. Because aircraft fly inside the fluid atmosphere rather than touching the ground, their fate depends on their heading. A commercial airliner traveling west slams head-on into a wall of air moving at supersonic relative speeds, subjecting the airframe to aerodynamic forces far beyond its structural limits. An airliner flying east is caught in extreme velocity mismatches and violent turbulence that strip away its flight control surfaces. Simultaneously, the Coriolis effect, the rotational force driving global atmospheric circulation,
drops to zero, causing planetary pressure cells to collapse instantly and unleashing violent barometric pressure drops across weather fronts. Across coastal regions and river valleys, water systems react with devastating force. Giant hydroelectric dams fracture under the sudden kinetic impact of their own reservoirs, unleashing inland deluges down inhabited valleys. Subsea fiber optic cables, tightly anchored across continental shelves, snap under seabed mudslides and crustal strain, severing the physical backbone of the global internet in a single second. At nuclear power stations worldwide, automated emergency protocols immediately trigger scram sequences, dropping control rods into reactor cores. But mechanical safety systems cannot save shattered buildings. The massive concrete cooling towers, fluid supply pipes, and backup diesel generators are sheared off their bedrock foundations, leaving facilities without external cooling loops or emergency power, initiating critical cooling loss across global nuclear infrastructure. If you look past the churning, dust-choked sky, orbit presents a haunting contrast. Low Earth orbit satellites remain in motion, held by gravity in continuous freefall, regardless of whether the crust spins beneath them. But geostationary satellites, locked 36,000 kilometers directly above specific points on the equator, suddenly watch the planet freeze beneath their sensors. Ground telemetry stations are swept away, instantly severing satellite navigation networks, military command links, and global telecommunications. Deep beneath our feet, a subterranean nightmare unfolds. While the solid mantle locks, Earth's liquid iron outer core obeys fluid inertia and continues to churn. The mantle and the liquid iron sea clash violently along the core-mantle boundary, generating immense subterranean friction. Yet because this subterranean dynamo keeps moving, Earth's protective magnetosphere would likely persist during these 5 seconds, sparing the surface from lethal solar radiation, even as internal friction superheats the lower mantle. Back on the surface, the oceans arrive. Seawater is a dense fluid with immense inertia. As the ocean beds freeze, billions of tons of water slosh eastward at jet engine speeds. Kinetic megatsunamis, hundreds of meters tall, sweep across coastal plains, pushing miles inland and grinding cities into underwater rubble. At the same time, the sudden stopping of the crust creates intense differential momentum against the semi-fluid mantle below. Global crustal stresses trigger widespread catastrophic earthquakes along major fault lines, tearing open colossal fissures across the fracturing landscape. Then, the timer reaches second 5. The planetary engine re-engages, accelerating the crust back to its original rotation speed of 1,670 kilometers per hour. This triggers the secondary kinetic impact. Every airborne structure, wave of displaced water, and piece of flying debris that was hurled east during the freeze is now slammed as the ground rushes back to meet it at supersonic speed. Ocean megatsunamis slosh violently backward across devastated continents, carving entirely new coastlines. And unless the kinetic energy transfer during this sudden restart is completely elastic, Earth's rotational momentum could be permanently altered, changing the length of the 24-hour day forever. 5 seconds. Not even enough time to draw a single breath. But in 5 seconds, the absolute laws of momentum reduce 300,000 years of human progress to dust. Nature feels no malice. It simply obeys inertia.